Welcome to the Problem Channel Season 3, Episode 47, the episode which I titled A Hidden Kepler or Isomorphism in Celestial Mechanics, because in this episode we will discover how a small and a seemingly simple and straightforward problem can encode several hundred years of mathematical battles that led to the development of modern celestial mechanics. But before we deep dive into the underlying matter, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page, find the episode titled The Problem Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And in the lightning round, who we are and what we do on this channel, we solve problems in mathematics, physics, and computer science in a happy and a never-ending chain. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on our channel that resonates with you, and then use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current supporters and current subscribers of our channel, especially those people whom I know personally from Quora. Thank you very much for your help and for your support. And as a small announcement, because lately I'm being asked on a regular basis, how do I use this channel still? In addition to the video explanation of how to use this channel that I explained how to get to, I've put together a written document, a free PDF file that is in my free GitHub repository, and a link to that file is in the comment section to this episode. I think that this file will be helpful for both the veterans and the newcomers to our channel alike, because it gives a very succinct and convenient way to perceive the channel at a glance. In the physics problem S3E47, we're given a point P that executes a circular motion over the periphery of a circle that has the radius uppercase R and the center C in such a way that its areal velocity with respect to the point O remains constant at all times. And under these conditions, we're required to find the velocity of the point P as a function of the distance rho, the distance between the moving point P and the point O, with respect to which the areal velocity of the point P remains constant. In classical mechanics, every moving particle can be associated with two parameters with absolute certainty: its location, tracked by the so-called radius vector of the point mass, and the velocity. This is no longer the case at a nanoscale. For example, in quantum mechanics, it is not possible to determine with absolute certainty at the same time both the location and the velocity of the moving particle, and that inability to do so is fundamental. In other words, if you think that this is just a matter of our ability to measure things, in other words, if we can fix a better device, twist some knobs or pull some levers and measure the location and the velocity of a quantum particle at the same time, this is not true. This inability to do so, like I said, is fundamental, and it's not a matter of our inability to produce a more precise device. But in classical mechanics, this is the case. Both of these parameters, the location and the speed, are known with absolute certainty. So what you should really know at this point, if you take on this problem, is the following fact. A radius vector of a moving point, let's say this is our point P, with respect to a certain origin that we chose for some fabulous reasons, then in a infinitesimally small amount of time, this radius vector will gain a small increment called v times dt, dt. In the time dt, this will be the small increment. In other words, the radius vector will move from this position to this position this way. And it is possible actually to assign a very interesting and meaningful physical quantity or magnitude to the area that is thus formed by the moving radius vector, precisely because, again, in classical mechanics, both the radius vector and the velocity can be known at the same time with absolute certainty. And in the classical Euclidean geometry, what is the area of this triangle? Well, one of the popular formulas says that the area of such a triangle will be the half product of the lengths of the sides times what? Times the value of the trigonometric function of sine evaluated at the angle between the velocity on one side and the other side. So in this case, we measure the angle between the radius vector and the velocity, and we take this area actually not only to be the area in the traditional sense, but we also assign another attribute, or sign, or direction. So this becomes signed area, and we define this area. Let's say we'll call it area as a vector. The infinitesimally small one will be 1/2 as a vector product between the radius vector and the velocity vector in the infinitesimal time dt. And that means that if we move the first differential from the right hand side of this equal sign to the left hand side, then we will have precisely our so-called areal velocity of the moving point with respect to a certain origin as the first time derivative of the area swept by the radius vector. And this is a very straightforward physical meaning of this thing. That much you should really know at this point if you're taking on this problem. But because kinematics usually is the first thing that is studied in college in pretty much any course, sometimes maybe the study of kinematics may be preceded by the study of statics, but usually kinematics is studied first because this is a study of motion of point masses, or just geometric points in a complete isolation from the underlying forces that may act on that point. So what you may or may not know is the following. The angular momentum, designated with L as a vector, defined, let's say, mass times also as a vector product of the radius vector and the velocity vectors, or you can call it, I call it a vector product, you can call it a cross product. I designate the vector product with the square brackets. You may designate it with a cross like this. It doesn't really matter. It does not change the physical essence of what is going on. Pick your favorite notation, pick your favorite terminology. The idea is that if we know that the angular momentum is thus defined, we compare two formulas, and what do we see? We can actually define the angular momentum in terms of the rate at which the area swept by the radius vector of a moving point changes as follows. We just have to multiply it by 2 times m times the derivative, first time derivative, let's say this way, of the, I'll put the point over here to save space, over the assigned area vector. Now the thing is, also the thing that you may or may not know is that in the central field, if the force that acts on a particle passes precisely through the pole of that field, that then the angular momentum will remain constant over time. It will not change. And what does that mean? Well, in the non-relativistic case, if the mass of the moving particle remains constant, which in relativistic case is not the case, but in the non-relativistic case, when the mass of the moving particle remains constant, then that means that the first time derivative of the assigned area will remain constant. And this means at least two things, because the vectors of radius vector and the velocity lie in the plane that is perpendicular to this vector. It goes, let's say, this way. This is our small increment as a vector, perpendicular. and this vector remains what it is, it doesn't change. That means that the plane in which the particle is moving and in which we capture the radius vector and the velocity vector of that point remains what it is. And that means that the trajectory of the moving particle remains what? It remains a planar curve. It may be closed, it may be not closed, it may be not closed in a finite area, or it can be not closed in an infinite area, but fundamentally the motion unfolds in this case when the angular momentum doesn't change over time in a plane. That's number one. Number two, that means that if the magnitude of this vector remains the same, then that means also that the radius vector of a moving point sweeps equal areas in equal times. And this is precisely what we're told in our problem. In our problem, we're told that the radius vector of the moving point P with respect to the specially off-center point O, that is distanced a units away from the center of the circle, remains constant at all times. So what does that mean and how we can capitalize on that? Well, this is a straightforward maneuver in physics. You will see time and again, many times over, is the following. The radius vector of our moving point with respect to the point O, the radius vector of the point P with respect to the point O can be represented as a scalar rho, the distance, which must be present in the answer. We're asked to produce the answer in that shape, times the unit vector along the distance, look at this, OP. So this will be our unit vector. You see, this is a straightforward maneuver. Now we bring in the definition of the areal velocity. Again, I will designate it as sigma. You can designate it any which way, doesn't really matter. Is 1/2 vector product of the radius vector and the velocity vector of the point. But in our case, the areal velocity with respect to the point O is designated like this. O will be measured by the radius vector with respect to the point O. This makes sense so far? Makes sense so far. Now, if we project our areal velocity as a vector on the z-axis, let's say we take x, o, y to be the plane of the board. This is where the motion unfolds. And then the z-axis will point perpendicular to it this way, looking at us. Then the projection of this vector onto the z-axis with respect to the point O, z. We know, we're told this is a constant quantity, sigma 0. We know what it is. And it will be 1/2 times rho times v times the sine of the angle between them. And what is the angle between them? Well, extend the line OP, construct the velocity vector. What is the velocity vector? Velocity vector is always tangent to the trajectory. What is the trajectory? Trajectory of the point is a circle. So our vector v, the velocity of the point P, remains tangent to the circle at all times. And that means that if we construct a radius connecting the point C, the center of the circle, with the point P at all times, the angle between the radial direction CP, let's put it this way, CP, the angle between CP and the velocity vector is pi over 2, this angle right here. So the angle of interest to us, if we slide the unit vector ER this way to the point P, so the vector will point this way, ER, then what is the angle between the radius vector of the moving point P relative to the point O and the velocity vector? It will be this angle right here. See this angle right here, theta. But look at this. What can we say about theta? In this case, it's a composite quantity. It will be pi over 2 plus, let's call the angle between our radius vector of the moving point with respect to the point O and the radial direction CP. Let's call this angle, we'll call it alpha. This will be alpha. So now that since we have this relation alpha, we can do one of the following two maneuvers. Look at this. We're asked to find the velocity of the moving point as a function of the distance rho. This formula already tells us that we are on the right track. Sigma 0, which constitutes the constant area velocity of the point P with respect to the off-center point O, is known, given, constant. This we need to play games, and this we need to play games with the angle. But what is the second, let's put it this way. We know right away from here that, let's write down the expression for the velocity. The velocity as a function of rho, the distance between the point P and the off-center point O, will be twice sigma 0 divided by rho times the sine of the angle theta. That's one result. What other mathematical material can we bring to aid in order to tie together these two magnitudes? We need to find the angle theta. We need to say something interesting. Well, look at this. From the triangle, I'll put it this way, right here, from the triangle, what triangle? OCP. From the triangle OCP, we can use what the law of cosines, according to which, what do we have? A square. A square is equal to rho square plus r square minus 2 rho r times the cosine of the angle alpha. This is the angle between them. Vertical angles, they are the same, alpha, alpha, but alpha dovetails into the magnitude theta, the angle between the unit radial vector of the moving point with respect to the point O and the velocity vector. So according to this, look at this, it doesn't really matter. If we compute the cosine of this angle alpha, it means that alpha is equal to what? Alpha is equal to theta minus pi over 2, and then the cosine of alpha will be the cosine of theta minus pi over 2. This becomes sine of theta, you see, this way. Or we can pull the same maneuver with this sine over here. It doesn't really matter. Pick your favorite. I will use this to put it over here. So now we have, look at this. A square is rho square plus r square minus 2 rho r times sine theta. And from this equation, it follows what? That the sine of the angle theta, directly, right away, we grab it, move it to the left-hand side, comes out to be what? Rho square plus r square minus a square divided by 2 rho r. You see, this is it. And now we put this expression for the sine back into this equation right here. So we have the velocity of the moving point as a function of rho will be 2 sigma 0 times 2 rho times r divided by rho times rho square plus r square minus a square. You see, this is very straightforward. Into this formula, we inject the right-hand side of the expression for the sine of the angle between the unit vector and the velocity. We observe that one copy of rho and one copy of rho cancel out. 2 and 2 become 2 times 2 become 4. So now we have our answer. Let's write it down over here. The sought after function velocity, as the parameter rho changes, the way it changes, we have the following result: 4 sigma 0 times r divided by rho square plus r squared minus a squared. This is the result that you saw just a few seconds ago. This is the answer that we were looking for. And let's say we pretend right now that sigma 0 is 1, r is 1, somehow a is some constant. So but basically, fundamentally, what we have over here, if we ignore these details, we have the function that looks like this. F of x is equal to, or let's say almost as, 1 plus x squared, see, rho squared. You know this function looks as follows, like this. And what it means is the following. Let's say this is x, this is f. When the distance from the moving point to the point O diminishes, when rho diminishes, then we're dividing our numerator by a smaller number. So that means that the result, overall ratio of fraction, grows. So the velocity of the moving point will be higher as it gets closer to the point O. Conversely, when the distance rho, or our argument x, grows this way, goes over here, then compared to this, see right here, this is the distance. This is how these things roughly, let's say, change. When the distance of the moving point rho approaches the other side over here, it grows to its maximum. So then we will be dividing the same constant numerator, whatever it is, by a larger number. So the whole fraction will be smaller. And that means that the velocity of the point in this region right here will be what? Smaller. So this point is not moving, our point P is not moving over the periphery of the given circle at a constant velocity. The velocity of our point changes with respect to the point O. So this is interesting. And now we think, in some sense, this problem was too simple. Why is that? Well, on the one hand, it so happens in my experience specifically that in this downpour of frighteningly scary and difficult problems, that once in a while there comes in an easy problem that gives you a break, that lets you catch your breath. But that's on the one hand. On the other hand, here we think, what else is going on in this problem, because the result is just way too interesting. And now we ponder, can we improvise a little with this problem? And it turns out, even the situation over here, something is moving relative to an off-center point. Turns out that yes, we can, and in a quite clever way. And the reason why we feel clever about ourselves, because if we move the point O with respect to which an interesting motion will happen to the periphery of the circle or radius r, and the circle that has the center at the point C, then what will happen? Right away we know. Well, what will happen is that we will have Euclid's Elements book 3, proposition 20 on our side. In any circle, the angle at the center is double the angle in the circumference. If both angles have the same circular arc as their base, and in our case they do, look at this. We invent the following, or improvise with the following problem. We take our favorite circle and we claim that the circle is what? A thin but firm wire, metallic wire, is bent into. So we have a metallic wire, the shape of a circle of radius r, and we put a point on the periphery of that circle, the point O, let's say over here. With respect to this point, we have a rod. This is a rod, metallic rod, a rod that rotates about the point P with the constant angular velocity, omega 0. We know what it is. So this guy runs this way, let's say, with a constant angular velocity that rotates about the point O. See, it rotates this way. So far, so good. And it makes one complete revolution. And the angular velocity of this rod with respect to the point O is constant and known, omega 0. Now, the two objects, the metallic circular wire and the metallic rod that rotates at constant angular velocity, are joined in a holy matrimony. They're brought together by a small ring, metallic ring, through which the rod passes. And now we want to see that if the rod rotates, as the rod rotates, the ring will also run along the circular wire. So we want to know what is the velocity and the acceleration of that ring. And if we do precisely that, as I showed over here, we will measure the angular displacement of our ring with respect to, let's say, positive branch of the real axis of the x-axis with the angle. This will be angle alpha. You see, so far so good. So we know that with respect to the angular velocity in general, the angular velocity is defined which way? As the first time derivative of the corresponding angle. And then if we separate these variables, treating it as a trivial differential equation, then we'll have d theta equals omega dt. If omega is a certain function of time that in this case would need to be given to us, then we will have an interesting time integrating this equation. But if we integrate both sides from theta 0 to theta and then from t0 to t, then we will have an equation that connects somehow the angle that tracks the change of our rod, let's say, about a certain point, and the angular velocity in time. But in this case, let's say angle theta 0 will be 0. Some angle will be non-zero angle will be theta. The t0 will be 0, and omega is omega 0. So in this case, from here we will say that once we integrate this, we'll have theta is equal to omega 0 t. We know this as a function of time. Theta is t. That is wonderful. And then what do we have again? By Euclid's Elements Book 3, Proposition 20, the way we concocted or improvised with the whole setup, with the rotating rod, the cleverness of this arrangement, we feel good about it, is the fact that the angle at the center, this angle alpha, is twice the angle in the circumference, because they have the same, see, they have the same circular arc as their base. So what can we say by this? By this proposition, we have alpha is 2 times theta, and this will be 2 times omega 0 t. The velocity of the ring, as it slides along the circle, will be omega r. The angular velocity of our circle with respect to the point C. This will be d alpha over dt times r. This will be d twice, let's say twice theta over dt times r, and this will be, we differentiate 2 omega 0 t over time, we get twice omega 0 r. So we feel good about ourselves. The velocity of the ring will be 2 omega 0 r. This is our first result, but it is important to understand that in this case, look at this. It is a constant quantity. We have the motion that somehow unfolds with respect to an off-center point O, but this time the velocity, the linear velocity of the point, is a constant. In the previous problem, we proved that this velocity with respect to an off-center point was not constant. It's faster when the point gets to the center, off-center point O, slower when it's on the opposite side. Wonderful. So now that we know that the velocity of the ring is constant, what can be said about the acceleration? In general, the acceleration, the complete acceleration, is the vector sum of normal and tangential tau accelerations. But look at this. The tangential acceleration keeps track or changes what? It changes the magnitude of the velocity vector, but not its direction. And the normal acceleration keeps track or changes the direction of the velocity vector, but not its magnitude. We proved that the magnitude of the velocity vector remains constant at all times. So the tangential acceleration in this case vanishes. So the only non-trivial contribution that will be made for complete acceleration will be the normal acceleration. Right? So This means that our acceleration will be normal v squared over r. And what is this? Look at this. 4 omega squared 0 r squared, one copy of r in the denominator. So we have 4 omega squared 0 divided by r. Let's write it down this way here. And this is also a constant quantity. But now we step back from our little improvisation and think, that was too easy again. Can we drill a little bit further into this problem and figure out, let's say, task ourselves with computing the areal velocities of the ring relative to the center of the circle C and the O center, point O. To omega 0, which is a constant. Very well. A few seconds ago in the previous segment, we computed the linear velocity of the ring as twice omega 0 r, which is a constant quantity. Omega 0 is the angular velocity of the rod that rotates about the point O with constant angular velocity. And then the angular velocity of the ring, here I distinguish it from omega 0 with the subscript c to designate the fact that this is the angular velocity of our ring relative to the center of the circle. The first time derivative of the angle alpha, which is what is the central angle that has the same base as the angle in the circumference. Euclid's Elements, Book 3, Proposition 20. Central angle is double the angle in the circumference, provided that the two angles have the same circular base. They do in our case. So the first time derivative of twice theta over time, the first derivative of 2 omega 0 t over dt comes out to 2 omega 0. So the angular velocity of our ring comes out to be constant. Now we task ourselves with computing the areal velocities of the ring relative to the center of the circle and to the O center point O. In the first case, this is a trivial computation. The areal velocity relative to the point C in its projection on the z-axis that runs this way will be what? The radius vector r is a constant quantity, r over 2 times v times the sine of the angle between them. What is the angle between the radial direction and the vector velocity in this case, which is tangent to the circle at every point? Pi over 2. So this is pi over 2. So now we have it r divided by 2 times the velocity. What's the velocity? Times 2 omega 0 r times 1. 2 and 2 cancel out. We have omega square 0 r square. And this is another, look at this. This is a constant quantity. In other words, the angular velocity, the areal velocity of our ring relative to the point C is a constant quantity. You see, it's constant quantity. Now, let's compute the areal velocity of our point of the ring relative to the point O. Relative to the point O. This time it will be rho over 2 times v times the sine of the angle between them. What's the angle? Pi over 2 plus alpha. But these angles are vertical, so alpha is alpha. And in this case, the triangle OCP is isosceles, so alpha by magnitude is theta, the isosceles angle, the angles at the base equal. So if we project the center of the circle C onto the base OP, then what is the expression for rho? Twice the projection of the radius on that base. So this will be pi over 2 plus theta, as we proved. So here we will have, let's write down the expression for rho. It will be 2 times r times the cosine of the angle theta divided by 2 times, what is the velocity? 2 omega 0 r times, well, what is this? For all theta real, this becomes the cosine of theta, you see? So this will be cosine of theta. So what do we have? 2 and 2 cancel. R and R become squared. So let's write down the expression for the areal velocity of the ring relative to the point z, and its projection on the z-axis will be 2 omega 0 r squared cosine squared. Oh, look at this, cosine squared. And theta, we already said that the theta is omega 0 t. Omega 0 t. Look at this. This is an interesting result. In this case, this tells us that this is not a constant. You see, the areal velocity of the ring with respect to an off-center point O is not a constant. It varies over time. As cosine squared, you can reduce the power, but it doesn't matter fundamentally. It is different. So now we go back to our original problem, and we juxtapose the angular velocities of the moving point in each case and their areal velocities. For a bit of wisdom that balances your academic life against real life, here are two facts that I established myself empirically, if you will, based on my experience in college. Doing homework is not only not equal to studying the subject, but this is strictly less than studying the subject. Likewise, getting good grades is not only not equal to knowing the subject, knowing versus studying, you see, but it's strictly less than knowing the subject. Even if you get good grades in the format of examination that was prevalent in my time. In my time, all the examinations in mathematics, theoretical physics, and computational sciences were in real-time, face-to-face verbal interrogation format. Even in this case, if you get good grades, it is still strictly less than knowing your subject, and the only way to begin putting the equal sign between them, is to start asking more questions by yourself. We're trying to run, in some sense, ahead of the train. And if you do not ask these questions, then these relations will hold for you for all time. Even if that after you graduate, this still will be the case. And many times you'll be stepping out of the boundaries of your homework and tasking yourselves with problems that you will not be able to solve most of the time, and that is perfectly fine. No one is born with the perfect ability to craft beautiful, crisp problems that have an academic solution, the clean garden path solution. But if you do not try to do that, then these relations will remain the same. So the point is, in order to somehow equate doing homework with studying the subject and getting good grades knowing the subject, is to start asking questions by yourself, show initiative, show improvisation, and step further. So in this case, we do precisely that. We compile a little table where we take our original problem, where the point was moving on a circle with the constant areal velocity relative to an off-center point, and our sister problem, in which we made a rod spin over a point on the periphery of a circle at a constant angular velocity, and we compare the angular velocities to areal velocities in both cases, because in this comparison we will hopefully gain some understanding. So what is the deal with the angular velocity in the sister problem? Remember, the angular velocity was twice the constant angular velocity of the rod, and that means it's a constant. And its areal velocity, we computed the areal velocity in our sister problem, was a variable quantity over time. It varied. But in our original problem, the areal velocity of the point relative to the off-center points in both cases, in the original problem, it was constant. So now, once we compile this table, the natural question, you see the natural question that leads you in the right direction. What will be the angular velocity of the point in the original problem? So how do we compute it? You see, this is exactly how these things work, and that is why I gave you a little bit of academic real-life balanced wisdom a few seconds ago, because at this point, once you showed initiative, constructed a related problem, and stepped outside of the boundaries of assigned homework, you develop a better feel for what is going on, and now you can compute the angular velocity of the point P with respect to the circle center C without any issues. You know that this angular velocity was designated with the subscript C just to make sure that we know what we're doing is the first time derivative of the angle theta over time, d theta over dt, and this is the angle theta. This time, to save space, to conserve space on the board, I compacted the drawing and I moved the pole of our point P to the right side over here, but it doesn't really matter. The trigonometry and the mathematics of this situation works out the same way. Anyway, so we have this, so now we need to somehow figure out, connect, elicit some information about the angle as its rate of change over time. See if we can do it. Well, how do we do it? Exactly, that is how we do it. We know that the areal velocity of our point with respect to the point O, the areal velocity of the point P with respect to the point O is a constant quantity. It's given over here. This is a constant, and we know what it is. But on the other hand, it will be what? 1/2 already times rho times the velocity of this point, times the angle, again, between times the angle between the velocity of this, the velocity vector of the point P and the unit vector. Again, we have the unit vector over here. You know the drill. We represent the radius vector as the scalar times the vector, this over here. So this angle right here will be what? Pi over 2 times sine of pi over 2 minus alpha. And for all alpha real, this becomes the cosine. So it will be rho over 2 times v times the cosine of angle alpha. You see, that's how it works. Now, the linear velocity v, is equal to, again, omega c times r. You see, this is how it works. This is how we splice the quantity that we need into the works. So here we continue writing. It will be constant quantity r over 2 times omega c times rho times cosine of the angle alpha. And what is the angle alpha? The angle alpha is the angle between the radial direction CP at any time and our direction OP, this one, this. So now look at this, how conveniently we have rho times the cosine of the angle alpha gives us precisely this projection of the distance rho onto the radius. So what does that mean? Well, let's put it this way. Our radius CP, that is distance between the point C and P, can be represented as the distance from the point C to the point A plus the distance from the point A to the point P. And what is the point A? This is the projection of the center O onto the radius. Remember this construct. We will come back to it in the Newtonian way of doing things in a few seconds. So this is it. And what is this distance CA? Well, this is the displacement A. Remember A, which in all fairness we take to be like this, less than R and greater than 0 in general, let's say. So here it will be A times the cosine of this angle right here. So this will be CA. It will be CA. So from here it follows that rho times the cosine of alpha is AP. This is this distance right here. This quantity is this guy right here, and from here it follows that AP is CP or R minus A times cosine of theta. You see, this is how we instantly arrived at this result. So now we have this, we have R over 2 times omega c times R minus cosine of theta, and this is equal to, don't forget, this is equal to sigma 0. So from here, from this relation, let's come over here and we will write it down as follows. omega c, the angular velocity of the point P on the circle, this time relative to the point C, just to make sure, is equal to, from here we have what? Twice sigma 0, that's the areal velocity of the point relative to the off-center point, divided by r times r minus a times cosine of the angle theta. You see, this is trivial. Now this already is d theta over dt, a very pleasant ordinary differential equation with separable variables. We separate the variables and prepare for integration. So here we have, look at this, 2 sigma 0 dt is equal to r times r minus a cosine of theta d theta. Integrate both sides from 0 to t on the left, and from, let's say, we will count initial angle theta at time t0 as 0, theta 0, so from 0 to theta, and this integral is trivial, so from here it follows that we have what is going on. 2 sigma 0 t is equal to, look at this, r squared theta is equal to r squared theta minus, we have the minus over here, the integral of cosine of theta d theta. This is a trivial integral. It is equal to sine, the trigonometric function of sine of theta, evaluated between boundaries 0. Sine at 0 is 0, sine of theta is theta, so minus a r sine of angle theta. So let's write down this equation over here in this form. R squared theta minus a r times sine of theta is equal to 2 sigma 0 t. You see, and now we came to the situation where we have the angle theta that shows up twice in our equation. Look at this. We deduced it in a straightforward manner using nothing but basic middle school arithmetic. Trigonometry is equal to, this is a function in time. However, this equation over here, known as a transcendental equation, which means that there does not exist a finite combination of elementary functions which allows us to write the angle theta as a traditional, again, finite combination of elementary functions as a function of t, of time t. This is the shape in which we have to leave, this is the shape in which we have to leave our answer. This is the shape in which we have to leave our answer. If you were able to move that far on your own, you're doing pretty good in physics. And we also have to bring in this equation over here. We have to say that the omega is equal to 2 sigma 0 divided by r times r minus a cosine of theta. So these two equations over here answer the question that we posed ourselves. What is the angular velocity of the point P that moves over the circle in such a way that with respect to an off-center point O, its areal velocity is constant? Well, here is the answer. This is the explicit function that captures the angular velocity of this point in the angle theta, in this angle theta right here, this angle. But the angle depends on time through this right here, transcendental equation, for which there does not exist a finite combination of elementary functions, that is, in t theta, in t explicitly cannot be written like this. Analytically, we cannot solve this equation. We have to use numerical methods. And now, the next thing that we do over here, okay, it depends on your personal problem-solving experience and the knowledge of mathematics, but what we do over here is a maneuver which precisely brings us to the point of this episode, a hidden Kepler and isomorphism in celestial mechanics. you're a student of physics who was able to take this problem this far, then you're doing pretty well. You may or may not know about the so-called Kepler's equation, which we will consider in a second. We all have different interests in physics and mathematics, so our personal experience will vary, personal mileage will vary, and to some extent your theoretical physics professor may give you this problem in order to see how students will react. Most students over here, of course, in the heat of the moment and the adrenaline rush to do the homework, solve this problem, possibly correctly, then they drop it on the floor cold turkey, step over it and move on, and this is in some sense perfectly fine. But remember my words of wisdom that you saw a few seconds ago. Doing homework is strictly less than studying the subjects. You want to always drill deeper, show initiative, paint yourself into a corner, create a problem, or come up with a problem that you cannot solve, that is beyond you, and that is perfectly fine. Only when you take on problems that you do not know how to solve, you will discover what needs to be discovered, you will learn what needs to be learned, and so on. This is how progress is made. So here, the next step is to multiply this equation through by the multiplicative inverse of r squared, and look at what happens once we do so. Here r squared cancels out, so we'll have theta minus one copy of r cancels out, so we have a divided by r times sine of theta, and on the right hand side we will have 2 sigma 0 t divided by r squared. So this is the equation that ties together the angular displacement of our point P with respect to the center C and time. This is the time evolution of this here angle. And look at this again. This seems to be very, at the beginning when we looked at this problem, very simple, straightforward, baby arithmetic. This is nothing complicated, but we're already in a small number of straightforward steps came into this equation over here. And the next step, again, depends on the level of your knowledge. Here we bring the so-called Kepler's equation. Kepler's equation, and we will write it down. I will write it down suggestively like this. Let's say I will use blue chalk over here. So it will be E minus. Let's use something for eccentricity. We'll use green. The eccentricity, E, not to be confused with the Euler's constant, times sine of E. Let's put it this way, and the whole thing is equal to, let me use red, m. So here in the Kepler's equation, E is called eccentric anomaly, m is called mean anomaly, E is eccentricity. Here is the same thingy, E, and all these quantities pertain to the orbit of the planet that is traced in a given system around the star. And now if we establish, look at this, we actually came across this in the end of season 1, where I framed this discussion back then in terms of mathematical equivalence, just to start things off. And we saw that the time evolution of a system that amounted to a small bead sliding off of a rotating rod, and the problem of, or the time evolution of the system of two armies which duke it out in the open field, described by the same differential equations. So in some sense, we could say that back then the two mechanical systems were actually isomorphic with respect to each other. So here exactly we have this isomorphism in physics, but isomorphism in physics imposes a little bit more requirements, and we'll get to the nitty-gritty of these requirements in a second. But look at this now. If we correlate, let's do this, we correlate our angle theta to eccentric anomaly, and this is precisely what in celestial mechanics is called eccentric anomaly, this angle right here, eccentric anomaly. And then we correlate this ratio, A divided by R. Remember, A is less than R, so this ratio is less than 1 to the eccentricity of the orbit. Now our angle theta over here is still correlates to eccentric anomaly, and this animal right here is correlated to mean anomaly. And this shows us that the equations of motion that trace the time evolution of a Keplerian planet over a Keplerian star, let's say with, over an ellipse in one of the two foci of which the star is located, this equation is identical in its structure to our equation that describes the time evolution of the point P relative to the point C. And that means that structurally, the motions of the point P over a circle in the described fashion, is the same as the motion of the Keplerian planet over the Keplerian orbit, over the sun, or over the star that is located in one of the foci of the ellipse. So that means that these two systems, the Keplerian planet that orbits the sun or orbits its star over an elliptic orbit, and our motion of our point over the circle, is these two systems are isomorphic, precisely because they're structurally they are the same structurally, but by the look on your face, I can judge that you're not entirely convinced. So for that purpose, we bring in Newton. How would Newton compute the areal velocity of the point P on the circle? Well, this is how. Newton would draw the center of the circle C, place the point O, about which our sample point P rotates about the circle in such a way that its areal velocity is constant here, the distance is here, this is our circle. Then to that point, through the line segment CP, Newton would construct a tangent. This is a key observation here, a tangent tau that is perpendicular to the radius CP at any time. And then Newton would pull out his usual infinitesimally small argument, and my personal opinion that Newton probably was the grandfather of the basic differential geometry, because he was a master of manipulating these infinitesimally small quantities. He would say that, okay, in the infinitesimally small amount of time, the point P would progress or move along its trajectory, the circular arc, into the point P prime. And by doing so, it would be displaced in angular measure relative to the center of the circle by the angle. What is this angle right here? It will be infinitesimally small angle dE. Remember that now we're operating in terms of eccentric anomaly. We do not call it the angle theta, we call it in terms of celestial mechanics, the terminology of celestial mechanics. This is eccentric anomaly, this is the angle dE. So now what is the area of this elementary little triangle? We treat it as a triangle. Well, traditionally, this is a basic formula, half the product of the base and the height. What is the base? The base we take to be the circular arc PP prime, infinitesimally small. This guy, let me write it down in blue so you see the association. This guy is RDE, the small angle. And what is the height? The height is the length of the line segment that we draw by constructing a perpendicular to the tangent tau through the point O. Perpendicular OH is the height of this triangle. That's it. This is the setup. It's not really complicated, and it's worth spending time to master Newton's method. So now we have 1/2 times R times dE. Now let's think about the height, this guy right here. If our radius CP is perpendicular to the tangent, and the line segment OH is perpendicular to the tangent, to the same tangent, because that's how we construct the height of our triangle, we have two parallel straight lines, OH, and let's call the projection of the point O onto the radius CP. Again, this will be our point A. This is the point A right here. See? This is the point A, projection of O onto the radius CP. So this line segment AP, and will be parallel to OH. This will be rectangle, and that means that since this angle is right and this angle is right, OH is equal to AP. So this times the distance between the points A and P, and now you see where this is going. 1/2 times R times DE. Now what is the distance from the point A to the point P? Well, it is the distance from the point C to the point P minus the distance from the point C to the point A. This is the same exact argument. The only thing that we changed over here is we introduced a little bit of this infinitesimal argument. This is the typical Newtonian style argument. So what is CP? The CP is R. This is R. And what is this? This is A times cosine of E. See this right here. So finally we have 1/2 R times R minus A times cosine of E, 1/2 times dE. I apologize here for the cramming. Like this, let's write it down more carefully. dA of the circle divided by dE. dE is equal to 1/2 R times R minus A times cosine of E. And you can already see that the structure of our equation is basically the same. If we factor out R, let's say we go like this, R squared over 2, then it will be 1 minus A divided by R times cosine of E, and this is it. This is the area of the circle. Not the circle, the area of the sector that is constructed based on the circular motion of the point P over its circular orbit. And if we take the expression that we developed for the infinitesimally small area of the corresponding sector based on a circle, DAC, with the subscript C designating the circle that we developed in the previous segment, divided by dt, we get by definition our constant areal velocity, and then again we separate the variables and we obtain the same equation, and this is how Newton would have done it. And once we integrate this equation through, we obtain the same result, and this is how we establish a bijection. The structure of our equations of motions is the same, and not only that, we explain how to map all the variable material between these two equations. So now the way in which these things, or this seemingly simple problem, connects to celestial mechanics is the following. Our circle is called the reference circle, and the way in which the actual physical location of the planet that traces an elliptic orbit with the star in one of its foci is obtained is the following. From this point P on the circle, which we know how this point moves now, we drop a perpendicular onto the straight line that connects the center of this ellipse and the center of the circle. Notice that the ellipse is the origin center, and this circle is origin center, and the large semi-axis of this ellipse is equal to precisely to the radius of this bounding circle. Now this straight line perpendicular to this straight line from C to O extended will intersect ellipse obviously at 2 points, but for the purposes of the upcoming bijection we're only interested in one, this point right here. So this is we will call the point A for the actual planet. This is where the actual planet will be located when it moves over the elliptic orbit. And the point P over here is, in some sense, a faithful shadow or image, if you will, of the planet that moves over an elliptic orbit that runs over the circular orbit. This is absolutely Marvelous. And then again, the point O will be called the orbital focus, the angle between the straight line CO extended and the direction from the star to the planet. This angle right here is called nu, and U for the Greek letter. And nu, this is called true anomaly. And this true anomaly connects, there is a way to connect true anomaly to the eccentric anomaly, E over here. This is the angle. You see, this is the clever bit that connects the motion of a planet over an ellipse to the motion of the corresponding, let's say we call it shadow planet, over the same origin-centered circle, the bounding circle or the reference circle that has its radius equal to the length of the major semi-axis of this ellipse. Again, the terminology by now you should be familiar with. E is called the eccentric anomaly, M is called the mean anomaly. And look at this, even from our equation over here, it follows that our equivalent of the mean anomaly is a uniformly growing angle, as if the orbit of the planet were actually a perfect circle, shown over here, as if, this is important, as if the planet's orbit were an actual circle. And then this angle will be, I did not show it over here in order to avoid the clutter, you understand, but it will run somehow here. This will be angle, this will be this angular measure that corresponds to M. You can see the diagram on Wikipedia, on Wikipage they have it. So, but once you look at the wiki page, you now understand, you will have a better understanding where all this material comes from. And now for the final bijection step, it turns out that in this particular case, it is possible to establish a bijection between the origin-centered ellipse and the origin-centered bounding circle, whose radius is equal precisely to the length of the large semi-axis. And this bijection, intuitively, even it's clear that this bijection is done as follows. If we want to biject a circle onto ellipse, we simply execute a uniform and continuous contractile of the plane only along the vertical axis, only along this axis. We do not even touch anything in the over the x-axis. It's a continuous and uniform contraction of the circle until it becomes an ellipse. And conversely, if we want to take, or biject, if you will, an ellipse into a circle, now we execute only one continuous and uniform transformation, is the expansion of the plane only along the vertical axis, let's say y-axis, if you will, until our ellipse grows into the circle. Mathematicians will call this a bijection. They will require a map, and this is a map. I've shown it over here. If xy is a point on a circle, then we replace, substitute x for x. You see, x does not change, but y is scaled by b over r. I do not want to introduce more information than we have to, because here in our problem we call this distance a. You see, it becomes transparent, the distance a. So let's say the length of the smaller minor semi-axis is b, so we scale it by b over r. And if xy is a point on a circle, meaning x squared plus y squared is a square, look at this. You see, this is r squared. Then if we construct the hopeful equation of the ellipse, what will happen? X squared divided by r squared plus y scaled by this factor right here, b squared over r squared, and in the at the bottom we put b squared. Here b squared and b squared cancels out, 1 over r squared factors out, 1 over r squared, and we get x squared plus y squared. But x squared and plus y squared is a point somewhere on the circle, px, y, you see. So the sum of x squared plus y squared is r squared and r squared in the numerator denominator cancel out. We get 1, and we have our equation of what? Of an ellipse. This is how we establish a bijection, and conversely, we can go through the same exercise, but it is important to understand that now the isomorphism, or let's say a bijection between a origin-centered ellipse and the circle that we established over here, is one thing. It's purely mathematical, but this is not enough for the isomorphism to take place in this particular case in celestial mechanics. but in general between two mechanical systems, because let's say, for example, we have this bijection, but the point P is moving over the circle, not at varying speed as we proved and computed in this episode, but let's say it's moving at a constant velocity. Then will these two mechanical systems be isomorphic? The answer is no. These two mechanical systems will not be isomorphic, precisely because even though their trajectories are bijective, we can biject one into the other, their equations of motion will be different, because we already proved that for true isomorphism to exist between these two mechanical systems, the point P has to move in precisely such a way, not a uniform motion. And in this case, there is a genuine isomorphism. But if the point P moves over the circle C with, let's say, uniformly with the same speed, the same angular velocity, then these two motions will not be isomorphic. And again, there is a tremendous power in finding isomorphic mechanical systems, because the way these things work, both in mathematics and in physics, let's say we have, just to give you an example, we have one group, let's say, for the sake of argument, because we can have two groups that are isomorphic, two graphs, two rings, two fields, two triangles can be isomorphic. Let's say we have a certain group, we're very familiar with the material that goes into the manufacturing of this group, we know it in and out, and then in another place we come across another group, and we're not very familiar with the material, but we somehow managed to prove that these two groups are isomorphic. Well, the way this power of isomorphism works is that all the results that we obtain based on axioms of a group only for one group, which we know well, can be lifted, shifted, and dropped onto the isomorphic group, and then translated into the language of that group, and then we will gain certain insight. We will gain a certain insight from this lift, shift, and drop. Same thing works in physics. Once we prove that two mechanical systems are isomorphic and we establish a mapping between the variables that go into a complete description of the time evolution of the system, we establish the bijection, we show that structurally these equations are the same, then all the results that we obtained in the study of one mechanical system can be lifted, shifted, and dropped onto a new system and adjusted accordingly. And we went through this exercise at the end of season 1 when we deduced the Lanchester's law of squares and looked at remember, there was a bead sliding off of the rotating rod, and we exactly established this bijection and showed how the power of isomorphism in mechanics or in physics in general can be exercised. And for now, this is it for the physics problem S3P1, and we will move on to a new challenge next. One more thing before we jump to the next challenge, the challenge in computer science. I would like to bring your attention to the fact that in this episode, what have we learned, amongst other things? The beautiful isomorphism in celestial mechanics, how things work. We learned that a seemingly small and simple problem can encode several hundred years of mathematical battles that led to the development of celestial mechanics. And again, like I said, obviously the person who constructed this problem knew his or her material exceptionally well. And again, it can be used as a test to see how students will react, who will say what, and which students will take this problem further and run with it and hopefully come to these equations that we developed on this episode. You cannot be doing this with every problem, but at least in the back of your mind, when you work on your homework problems, you should try to do that. And eventually, it's a good idea to develop a nose for beautiful problems when your gut is telling you, there is something interesting over here. This is entirely possible in the even the fierce schedule of college curriculum in a technical school. It is possible. I did it myself, so this works. Now, the next challenge will be a problem in computer science, S3CS11, and it will be based, as I promised, on the material of the previous computer science episode, where we solved the computer science number 10, where we discussed a practical big O1 algorithm, where we implemented basically a singly linked list whose memory store was backed by a fixed size array, and then we made a beautiful chase around this area where by flipping the pointers only. Flipping pointers is a big O1 operation. This doesn't cost really anything. Changing addresses of variables in real time when the program runs does not incur any major cost. So behind this idea, now we want to capitalize on this idea, and we want to discuss the following task. Implement a thread-safe fixed size queue that is based on the ideas that we discussed in the problem S3CS10 when we discussed the idea of a big O of one practical algorithm. And the requirements for this fixed size queue should be the following. Your code should block forever, because adding timing is of course possible later, but we do not need that for now. Let's say block forever if the queue is empty and someone is asking you to remove an item from the queue. And you also should block if the queue is full when someone says put one more item into this queue. So implement these two requirements: block if empty on queue remove, and block if full on queue add. Make it thread safe. Choose any language of your liking. I will of course I'll show my implementation of this queue using the best programming language of all time, C. But for now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the computer science problem, S3CS algorithm.